Hello, everyone. This time I'm standing outside of 3 Mile Island, the site of our own nuclear meltdown here in the US. It took place back in 1979 in Pennsylvania. So while Chernobyl was by far the worst nuclear meltdown experienced on this planet, we here in the US aren't without our own nuclear mishap. And so today, what I want to talk about was nuclear decay, and more specifically, the relationship between mass and energy. So let's share the screen and get started. That's it. That's it. Okay. All right. So a few questions here, right? Why does radioactivity even occur? Right? What causes some particular nuclide to be radioactive, in the first place? Why do some nuclides decay using alpha decay, while others decay using beta decay or positron emission, like we talked about a couple lectures ago? So far, we've certainly talked about these different types of radioactivity, um, but we haven't really got into what causes radioactivity really to begin with, right? And the answers to these questions aren't simple, right? We can get a basic idea, however, of the factors that influence whether or not a nucleus is stable, and what kind of decay it is going to undergo by understanding a little bit about the nucleus in general. And of course, what you guys have learned back in Chem 100 or Chem 101 is that a nucleus is comprised of the protons, which are positively charged, and the neutrons, which are neutral or not charged, right? And we know that positively charged particles, just like negatively charged particles, are going to repel each other. So protons in that nucleus are repelling each other. So what binds them together in the nucleus? Well, that is a fundamental force known as strong nuclear force. So that's the force of attraction between the nucleons that hold the nucleus together. So all the nucleons, the protons and the neutrons, are attracted to one another by these strong nuclear forces. Now, as it turns out, strong nuclear forces only act on very short distances. And luckily, an atom's nucleus is so tiny that the distance between those protons that are repelling each other happens to be very minimal. And so these strong nuclear forces can apply to that distance. And so if we think about the stability of a nucleus as a balance between these repulsive forces happening between the protons and the attractive strong nuclear forces among all the nucleons, then that can help explain why it is that the nucleus stays together, and why it is, as I'll talk about in just a minute, why nuclei don't stay together. And um, so um, so the neutrons in a nucleus, therefore, do play an important role in the nucleus. Even though they're not charged, they play a role in stabilizing the nucleus because they help attract the other nucleons, the other protons really, through this strong nuclear force. But they lack the repulsive force associated with the positive charge of the protons. So they're contributing the strong nuclear force attraction, but not also putting into the mix a repulsion like the protons do. So one might say, well, why don't we just add more neutrons? Why wouldn't that just lead to greater stability? The more neutrons, the better, right? That's not the case, really, because protons and neutrons, much like electrons, occupy energy levels within that nucleus, just like electrons occupy energy levels outside of that atom within the nucleus, outside of that nucleus within the atom, right? So as you add more and more neutrons to the nucleus, they occupy increasingly higher energy levels within that nucleus, and at some point, the energy payback, if you will, that they contribute via these strong nuclear forces aren't enough to compensate for the high energy demand that they are requiring to stay in these energy states that neutrons have to occupy. Okay. And so what happens is that they will start to break down. They will not be considered stable. And we look at this and we relate the number of protons and neutrons in a nucleus in such a way that we call it a valley of stability. Okay, and so it's very important to look at the ratio of neutrons to protons, or the NZ ratio, if you will. N being the number of neutrons, Z being the number of protons. Because that ratio is what's going to determine whether or not that nucleus is stable. And if you, let's see, annotate here. If you look at if you look at these green dots here, all along this diagonal flare, the green dots are going to represent stable nuclei. Okay, that is the valley of stability. And what you'll notice is down here, with these smaller nuclei elements, or these lighter elements, the ratio of N over Z, or the number of neutrons to protons for these lighter elements with stable isotopes is going to basically be equal to 1 right here. So the N to Z ratio, when it equals 1, you have this slope, this line. And as you can see, these lighter elements follow that trend pretty closely. So for instance, carbon-12, which is the most stable, most abundant isotope of carbon, is going to have an NZ ratio of 1. It's going to have 6 protons and 6 neutrons. Hence, that's why it's carbon-12, right? But then watch what happens so if we start going beyond 20 for Z, so beyond 20 protons, the NZ ratio of stable nuclei begin to get larger. See? So it's not following that 1-to-1 ratio. It's a little bit higher than that. And by the time you get to Z40, right here, so Z is 40, right there, the N is going to be 50. And now that ratio is more like not 1, but like 1.25, right? And then interestingly, once we get out to a Z of 80, so right here, Now the ratio increases even more to 1.5. And then you'll notice that beyond 80, really beyond 83, the green dots go away. Well, what does that mean? That means beyond 83 protons, which happens to be bismuth, stable nuclei just don't exist. Okay, so bismuth is the heaviest element with a stable, non-radioactive isotope. Beyond that, you start getting into just radioisotopes being the only flavor. And so if there are too many neutrons, what type of decay could we predict? And conversely, if there are too many protons, what kind of decay would we predict would be the outcome? Well, the type of radioactivity emitted by a nuclide depends, at least to some extent, on this ratio, this NZ ratio. So if the NZ ratio is high, meaning it's out here somewhere, it's above the valley of stability, that means it has too many neutrons, right, in that ratio to be stable. And so it's going to convert the neutrons into protons via, remember, beta decay. Okay, so when this process occurs by which beta decay moves the nuclide down in the plot closer to the valley of stability, what you're doing is you're essentially converting neutrons to protons, right? And so that ratio gets tighter and it gets closer to 1 to 1.5 range. Okay. Now, what if the NZ is too low, meaning now we have more protons than neutrons? Well, now we can expect that to be a positron emission or an electron capture decay. And what that's going to do is that's going to convert the protons into neutrons and bring that ratio back up, right? Now, in some cases, alpha decay also can raise that ratio from down here to up here. So alpha, when that NZ ratio is less than 1, but not to the same extent as positron emission or electron capture. Okay, let's clear this stuff. All right, now most nuclei don't just have one decay event to reach stability. Most of them have to go through a series or a decay series in order to reach finally a nucleus that is stable. Okay, so like I said, atoms that have more than 83 protons are all going to be radioactive, and they're all going to decay in at least one, most likely multiple steps involving alpha and beta decay, some gamma decay, of course, to carry away excess energy. But if we look at uranium-238, for instance, so, oops, sorry, annotate, there we go. So if we look at uranium-238, it's got 92 protons and then 238 nucleons. That is going to break down into thorium-234, but it turns out that thorium-234, that daughter nuclide, is also radioactive, okay? And so it's going to emit beta rays and decay into, uranium-238 decays into thorium-234, and then that is going to decay further into protactinium-234. Now, guess what? Protactinium-234 is also radioactive. So that's going to go on to another decay. And so if we look at this graph here we have uranium-238. It breaks down into thorium-234, which breaks down into protactinium-234, which then breaks down into uranium-234. And then that breaks down into thorium-230, and so on and so forth. And then remember radon-222, we talked about that last time, because uranium-238 is present in the soil and in rock and up here in Tahoe in the granite, and it breaks down into radon, and radon is a dense gas that can collect in your basement, right? And so again, it's going to go series by series, step by step, until it can reach some type of nuclide that's stable. And in this series, it happens to be lead-206 right there. Okay. And so that's what we call a decay series. Now, it turns out that not only is there a valley of instability, but there are also islands of stability. Okay, what's that about? Well, in addition to this NZ ratio that I just talked about, it turns out that the actual number of protons and neutrons also affects the stability of a nucleus. Okay, so interestingly enough, it happens to be that if you have an even number of protons and an even number of neutrons, right here, even and even, if that combination exists in a particular nuclide, that's going to give you 157 stable nuclides. Okay, so this is the number of nuclides, that's the number of stable nuclides. So by far, the most favorable configuration is to have even protons and even neutrons. Whereas if you have a nucleus that has an odd number of protons and an odd number of neutrons, you're going to have much fewer stable nuclides. Okay. And again, the reason for this is that these nucleons occupy energy levels within the nucleus, like I said before, like electrons do, right? And so just like atoms with certain numbers of electrons are uniquely stable, think aka noble gases, so too are atoms with certain numbers of nucleons. Okay, and in this case, the protons and the neutrons can be like 2, 8, 20, 28, 50. Those happen to be uniquely stable. And in a way that we refer to them as magic numbers, okay? As unscientific as that sounds. So these magic numbers of protons and neutrons that also contribute to nuclear stability. And again, these magic numbers are going to be even, okay? And so that is why if you were to study all the different radioisotopes, you would find that there is this abundance of stable nuclides with even numbers of nucleons. Now, these nucleons also have a tendency to pair together, much like electrons pair together. So within that nucleus, the nucleons are pairing, the protons and neutrons. And this tendency also results in a stability of the overall nucleus. Okay. So that's that's kind of where we stand with why uh, nuclei will undergo radioactivity to become stable. And these are some of the parameters that dictate that. What I want to do now is transition into the next part of the topic of this lecture, and that is really looking at this relationship between mass and energy. So we talked about nuclear fission and a little bit about fusion. And I mentioned at the very first lecture that fission produces a very tremendously high amount of energy compared to just like chemical reactions like combustion and stuff. Where does that energy come from? Why does that energy come forth? It turns out that the energy of the reactants, not the energy, the mass of the reactants is greater than the mass of the products. So if we have, if we have uranium-235 breaking down into barium and krypton, if we took the total AMU based on the uranium-235 itself and the particles, we could then say that it's 236.05258 AMU. And if we then looked at the products of that radioactive decay, right, and we added all them up, it's 235.86769. Now, what's happening there? Mass cannot be destroyed, right? And it's not. What's happening is that mass, that reduction in mass, is because a little bit of that mass has been converted to energy. All right? And that's why the splitting apart of nuclei lead to tremendous amounts of energy. If you extrapolate that out to a number of like a mole of uranium. Let's clear that. Okay. And this is because, again, mass is related to energy. And we can also account for this not just by looking at new radioactive decay, but if you were to look at the AMU of proton, getting ahead of myself, of protons, right? So 1.007276, and the AMU of neutrons 1.008665. And you said, okay, well, I want to see what the mass is of oxygen. It has 8 protons and 8 neutrons. So I'm just going to take those numbers and multiply by 8 and add that up. I get 6.127582 or 16.127582 or 16.13. But if you were to look at the mass of oxygen of the nucleus itself in totality, not by adding up the individual protons and neutrons, if you look it up in the periodic table, it's going to tell you that that is 15.99 AMU. Now, what's going on? Is this just people using different math? I mean, that's close, right? 16.13, 15.99. Close, but it's not a mistake. It is a mass defect. Okay, the mass defect is the difference between the total mass of the individual nucleons, right? So this and the nucleus as a whole. That right there. Okay? That and that difference, when you subtract those two from each other, that is what we call the mass defect. All right? And as it turns out, um, the amount of energy required to keep a proton or neutron in the nucleus is the same as the amount that is released if the proton or neutron is removed. And a guy by the name of, maybe you've heard of him, Albert Einstein, came up with a beautiful equation. Maybe you've heard of it. E equals mc squared. Of course you've heard of Albert Einstein. Of course you've heard of this equation. It's the most famous equation in history, I think. But to really understand it and know what it's saying, not just energy equals mass times the speed of light squared, right? Or the speed of light in a vacuum. The implications of it are so elegant and beautiful that it really is, to be able to express something with such a simple equation is really quite stunning to me. So what it's saying, E equals mc squared, is basically that mass and energy are interchangeable. Okay. And we talk about the nuclear binding energy, or the binding energy, being the amount of energy required to remove nucleons from a nucleus. And remember, that energy is going to be equal to the amount of energy required to keep it in the nucleus. All right. So in summary, the mass defect is the difference between the mass of the components, the protons and the neutrons, and the mass of the nucleus itself as a whole. And the energy that corresponds to the mass defect is the energy that holds the nucleus together. Pretty cool, huh? Now, what we can do is we can look at the difference in mass, or this mass defect, to calculate how much energy is released when the protons or neutrons leave. Okay. And we can see how much energy is released per mole of uranium, for example. Okay. Not just how much energy is released from a nucleus, but you can, of course, extrapolate that out further into a given amount, right? So how would we do this? Well, for one, we'd have to figure out what the mass defect is. And to do that, you have to look at the AMU of, in this case, uranium, which is 236.05258 and 235.86769. So you subtract those two, and that gives you the mass defect in AMUs. But of course, we want to now convert it to mass, because E equals mc squared. So we have a little handy dandy equation down here at the bottom that says that 1 AMU is equal to 1.66054 times 10 to the negative 27. What's that? That's a conversion factor. Okay, so we can use that to convert the mass defect into just mass, times it by the speed of light squared. So what's the speed of light? 2.9979 times 10 to the 8th meters per second. And that will give us joules. Okay. From there, you got to convert joules to, what do we want? They want moles to give you joules, how much energy per mole. So pause it here, see if you can, if that description made sense, and see if you can set it up and figure out what the answer is to this. And if not, just hang tight and we'll go over it in just a minute. Okay, so to start with, we have to figure out the mass defect. And it was, let's see, for that problem, we said that for uranium-235, it was 236.05258. And so then we subtract the, so that's the mass of the reactants. We subtract the mass of the products, 235.86769, and we get 0.18489 AMU, okay? Now we got to convert that AMU to kilograms. And remember that conversion factor is 1 AMU equals 1.66054 times 10 to the negative 27 kilograms per 1 AMU. And now the AMUs cancel, right? And we get 3.0702 times 10 to the negative 28 kilograms. Okay. And so that's going to be our mass that we pop into the E equals mc squared. Do different colors, go to red. So E, which is what we want to solve for, right? The energy, E equals 3.0702 times 10 to the negative 28 kilograms times the speed of light squared, which I said was 2.9979, not 710, where that came from, 9979 times 10 to the 8th meter per second squared. Okay. And that should give us 2.7593 times 10 to the negative 11 joules. But of course, they want how much energy in a mole, right? So what is this? This is joules per, technically, joules per atom. That unit's not in here because, but we know that it's per atom because that's what we're getting the mass defect of just one atom, right? So how can we figure out moles? Well, what is an atom? How many atoms are in a mole? Avogadro's number. So we take this and we multiply it by 6.0221 times 10 to the 23rd atoms per 1 mole. And that's going to cancel our atoms and give us joules per mole. And that ends up being 1.6617 times 10 to the 13 joules per mole of U-235. Okay. Now, that's one way to do it. Another kind of shorthand way to do it is to skip the Avogadro's number thing and skip the initial conversion factor right here, okay? We don't really need to do that because what is AMU? AMU is grams per mole, okay? So if we were to just, I'm gonna erase this. if we were to just take this number and say that equals 0.18489 grams per mole, it's kind of showing up, then all we need to do is just convert that to kilograms, okay? And so if we convert that to kilograms, that would be 0.000184889, right? Or what? 1.8489 times 10 to the negative 4. Grams, right, per mole. No, kilograms per mole. And so if you take that and then multiply it by the speed of light squared, it should give you the same answer. And then you don't have to do the conversion factor of AMUs to kilograms and then the conversion factor of atoms to, and the Avogadro's number to get to moles. Okay. So a couple different ways. I gave you the first way because that kind of shows you exactly what's going on using the conversion factors, and this is a way to kind of sidestep that and do it more quickly. Okay. Where is my screen? What's going on? Where is it? Share screen, but where is it? There it is. Okay. Now, all right. So that's how much energy is released, and I mean that's a lot. 1.6617 times 10 to the 13 joules. That's like about, what is that? 17 billion kilojoules, right? And highly exothermic chemical reactions produce upwards of 1,000 kilojoules per mole. So as you can see, fission is orders of magnitude better at producing energy than chemical reactions. Now, we typically report energies in joules, but nuclear physicists often use electron volts or mega electron volts. And 1 mega electron volt is equal to 1.602 times 10 to the negative 13 joules. So there's one conversion factor. And unlike energy in joules, which is often reported per mole, like we just did in that last problem, energy in electron volts is usually reported per the nucleus. All right. So a particularly useful conversion factor for calculating and reporting the nuclear binding energies is looking at AMU and mega electron volts and saying that 1 AMU is equal to 931.5 mega electron volts. Okay. So using this conversion factor, we can readily calculate the binding energy of, for instance, helium. Okay. So here's looking at the helium mass defect. So subtracting the, this must be the sum of the nucleons minus the mass of the overall nucleus, and you get 0.03. And so you can take that and look at the nuclear binding energy by saying that it's 0.03038 AMU, and then multiply it by that conversion factor right here, 931.5 mega electron volts per 1 AMU, and we end up with 28.30 mega electron volts for our nuclear binding energy. Okay. But in order to compare that energy to other nuclei, we calculate the binding energy per nucleon. Okay. So that would be dividing, so that would be taking this 28.3 mega electron volts and dividing it by 4 nucleons, because that's how many, 2 protons, 2 neutrons in a helium atom nucleus. And that gives you 7.075 mega electron volts per nucleon. Okay. And we can do this for other, nuclei in the same way, right? So if we looked at carbon 12, and if we said that that was 7.680 mega electron volts per nucleon, that's higher than helium, right? 7.680 is higher than 7.075. And since that binding energy for carbon 12 is greater than helium 4, we can conclude that carbon 12 is more stable because it has lower potential energy, okay? Because it has higher overall energy. That makes sense. So with that in mind, let's take that problem, well, I guess it wasn't really a problem, but let's take these tenets here that we learned and apply them to this problem here. So look at the, figure out the mass defect and the binding energy for helium-4 in terms of joules per mole, joules per nucleus, and mega electron volts per nucleus. Okay. Now the mass defect, again, we once you pause it and work on it, you already have the mass defect right there. But you can use the approach of doing the 1 AMU equals 1.66054 times 10 to the negative 27. You can take that approach, or you can just convert, you can straight up convert the AMUs of the mass defect to grams per mole. I don't care how you do it, it's up to you. But pause it, give this problem a shot, and we'll see what we can come up with. Okay. So to start off, we take E equals mc squared, and I didn't do the conversion factor of AMU to kilograms. I just took that mass defect and applied that to kilograms per mole, because it's, what was it? It was 0.0304 AMU, so that'd be grams per mole. So that turns out to be 3.04 times 10 to the negative 5th kilograms per mole. And we multiply that by the speed of light squared, 2.9979 meters per second squared. And you get 2.73 times 10 to the 12 joules per mole. So that's the first part. That's A, right, where they're asking for joules per mole of nuclei, right? Now, to get to B, what are they asking for B? Joules per nucleus. Okay. So now we can take this number and convert it to joules per nucleus by using Avogadro's number. So we could say 2.73 times 10 to the 12 joules per 1 mole times the conversion factor, 1 mole over 6.0221 times 10 to the 23rd, right? Avogadro's number. And if we do that, we, hold on, so 2.73 times 10 to the 12 divided by 6.0221 to the 23rd. I get 4.53 times 10 to the, what is that? -12 joules. Okay. Per nuclei, basically. So 4.5, that's a little fuzzy there, 4.53 times 10 to the -12 joules per nuclei, which is what they're asking for in B, right? And then for C, they want mega electron volts per nucleus. So remember what that conversion factor was. We said 1, let's do it a different color for each. So we said that 1 mega electron volt is equal to 1.602 times 10 to the -13 joules. Okay, so all we have to do is multiply this number, 4.53 times 10 to the -12 joules times that conversion factor, right? So one mega electron volt over 1.602 times 10 to the -13 joules. Cancel our joules. And what does that give us? That divided by 1.602 times 10 to the -13. I'm getting basically 28.3 mega electron volts. Okay. Straightforward, right? That's it, really. That's how it's done. Where is my, how do I get to share my screen? Where was it? Here it was. Okay. I think I had one more problem in here, right? Did I? Yes. So last problem, and then we'll call it, stick a fork in it. We're saying calculate the mass defect and the nuclear binding energy per nucleon. So in millielectron volts for carbon-16. That's the radioisotope of carbon-12. And it has a mass of 16.014701. Okay, so keep that in mind. What you have to do is you have to find the mass defect, right? By taking the mass of the protons, right? So the AMU, the 1.007276 times 6, and then take the neutrons, 1.008665 times not 6, but 10 in this case, because it's carbon-16. Okay, and then subtract from that 16.014701 AMU. That gives you the mass defect, and then convert the AMUs to mega electron volts. Here, I don't know why I have the speed of light. It must be just a carryover from the last one. But if we look here, where was it? Yeah. What's that conversion factor? 1 AMU equals 931.5 mega electron volts. So that's the conversion factor to go from AMU to mega electron volts, and then that's it. So pause it, see what you come up with, and then we'll see if it jives with what I come up with. Okay, so when I took 6 times the mass of the protons plus 10 times the mass of the neutrons, and I subtracted from it 16.01476, I ended up with 0.115546 AMU. That's the mass defect. And in order to, so that's the first part. Then to order to find the nuclear binding energy, we just convert the mass defect into mega electron volts. And we said that 1 AMU equals 931.5 mega electron volts. That is our conversion factor, right? So it's this times 931.5 mega electron volts over 1 AMU. That should say 931. And let's see, do that. Oops, 0.115546 times 931.5. I get 107. So that equals 107.63 mega electron volts. Okay. But remember, we have to look at it because it says per nucleon, right? The nuclear binding energy per nucleon. And so how many nucleons are in carbon 16? 16. So we take this and divide it by 16 nucleons. So 107.63 divided by 16. And I'm getting 6.73 mega electron volts per nucleon. Okay. That's it. Not too bad. Getting back into calculations. It's been a couple lectures. Next time, we'll finally get into the kinetics of radioactivity. And so more calculations, more fun stuff. And then that'll wrap it up. We can move on to organic chemistry, okay? But hopefully this made sense. If there's any questions, feel free to ask. I'll have a homework assignment that will have problems like this, the kinetic problems that you'll learn next time. But until then, have a good one. We'll see you next time.